Physicists measure the tendency of an object to want to rotate around a particular position with a quantity called moment. Actually, there are several kinds of moments, and we're going to talk about the first moment of mass. For a point mass whose mass is m, that is a distance x from the place where you want to know where it's rotating around, then the first moment is given by, so moment is capital M, and it's just the product of the mass and x. So if we have some mass over here, and we're measuring its moment about this point, and it's a distance x, then the moment is just x times m. Since the mass could be on one side or the other of the place of the axis where you're asking about, x could be positive or negative. You can see if we imagine that to the right of the axis to the right of your pivot counts as positive x values and to the left counts as negative. If you have a mass to the right-hand side, that's going to want to sort of rotate this way, so downwards on the right-hand side. So a positive moment will want to rotate that way, and a negative moment will want to rotate the other way, so it will want to pull down the left-hand side. So a moment really tells you sort of how and how much this whole configuration wants to rotate around your pivot point here. If you have several masses instead of just one, to find the moment of the whole system, you just find the moment for each individual mass and then add them all together. And the sum of the moments will tell you the entire system of multiple masses, whether it wants to tip one way or the other. So just to get used to this formula, let's find the moment of a 3 kilogram mass that's 2 meters to the right of a pivot. So we have some sort of pivot point. There's maybe some sort of balance beam that we're putting our masses on, and we're putting a 3 kilogram mass 2 meters to the right of the pivot. So the moment for this situation is the mass, which is 3 kilograms, times the distance to the axis, or the displacement from the axis, which is 2 meters. So that's 6 kilogram meters. All right. For a second example, let's say we have a 3 kilogram mass hanging from a rod. So here's the pivot point for the rod. The 3 kilogram mass hangs from a rod 3 meters to the right of the pivot. So say here's our 3 kilogram mass, and that's 3 meters. And a 5 kilogram mass hangs 2 meters to the left, like this. To which side does the rod tend to tip? So to figure this out, we need to find the moment about the pivot here. So we need to just find the total moment for this entire system. So for the first mass, the 3 kilogram mass, it's the mass, which is 3 kilograms, times the displacement from the pivot point, which is plus 3 meters. Okay, now we can add the moment for the second mass. The second mass is 5 kilograms times, and now we need the displacement from the pivot, which is 2 meters. But remember, it's to the left, and that counts as a negative displacement. So now we can do this arithmetic. We get 9 kilogram meters minus 10 kilogram meters. So we get minus 1 kilogram meters. So the moment of this whole system is negative, so that means that this rod is going to want to tip down on the left-hand side, not on the right-hand side. So if the moment is positive, the right-hand side wants to tip down. If the moment is negative, the left-hand side wants to tip down. And if the moment is 0, then it balances. Okay, so you could, since a moment tells us about sort of where something balances, you can actually use the moment to find the center of mass of an object. Let's see how that works. So the center of mass, if we have sort of masses distributed just along a single axis, say an x-axis, the center of mass of your collection of masses is the x-coordinate, which we're going to call x bar, It's the x-coordinate about which the moment of the masses is 0. So the masses would balance if you supported all of the whole system at this point. So let's suppose that we have masses that are located at masses 1 through n that are located at positions 1 through n. Let's find the center of mass along the x direction. So the only thing we know about the center of mass is that it's the x-coordinate about which the moment of the masses is 0. So let's write down what this says. Right? If x equals 0 is right here, say, right, we have a bunch of masses, all at different positions. Okay, so let's find the moment about the center of mass. So moment about the center of mass. It's the sum of each individual moments. So we have I from 1 to n. So we just need to add up the moments for each mass. So the mass of mass I is m sub I. And now we need to write down the displacement of this mass from the place where we're measuring the moment, which is the center of mass, x bar. So this is just x sub I minus x bar. If the mass is to the left, then this difference will, if the mass is to the left of the center of mass, then x sub I minus x bar will come out to be negative. And that's actually what we want because, mass to the left of the pivot counts as a negative displacement. So that's what we want. So here's the moment about the center of mass. But remember, the definition of the center of mass is that this moment has to be 0. So we can write 0 equals sum from I equals 1 to n of m sub I times x sub I minus x bar. Okay, well, if we actually have a physical system set up with masses lying around, then all of these masses will know, and all of these positions will know. The only thing in this that we don't know is the center of mass. So we can actually solve this equation for the center of mass. So let's do that. We get 0 is, let's see, we can distribute this mass, sum from I equals 1 to n of m sub I times x sub I minus m sub I times center of mass. Okay, now we can break this sum up over the difference. That's one of the properties of sigma notation, which, remember, just amounts to associativity and commutativity of addition. So we get the sum from I equals 1 to n of m sub I times x sub I minus the sum from I equals 1 to n of m sub I times x bar. Well, look, this piece that has x bar in it, let's move it to the other side of the equation, since x bar is what we're trying to solve for. So we get sum from I equals 1 to n of m sub I times x bar equals the sum from I equals 1 to n of m sub I, x sub I. But look, x bar, it's a constant. It doesn't depend on I. So it's a constant multiple, so we can move it outside of this sum. So we get x bar times the sum from I equals 1 to n of m sub I equals sum from I equals 1 to n of m sub I times x sub I. And now we can find our center of mass just by dividing. So this x bar, the x-coordinate of the center of mass, is the sum from I equals 1 to n of m sub I, x sub I, divided by the sum from I equals 1 to n of m sub I. Okay, fair enough. But this equation, it looks like kind of a mess, but let's interpret what this means. The denominators may be the easiest thing to interpret, because if you have a bunch of masses and you add up the masses, you just get the total mass. So the denominator here is just the total mass. The numerator, well, it's a sum, but look at each piece. Each piece is a mass times a position. And this position is measured, since it's just the bare x-coordinate x sub I, this position is measured from the x equals 0. So it's measured from the y-axis. So each one of these is a moment about the y-axis, and we're adding them all up. So this numerator is just the total moment about the y-axis, or the total moment about x equals 0. So the center of mass is just the total moment of all of your masses about x equals 0 divided by the total mass. That's something that we can actually work out. So let's look at an example. Let's find the center of mass of these objects. So we have a 2 kilogram mass placed at, so if here's x equals 0, we have a 2 kilogram mass placed at 3 meters. And we have a 5 kilogram mass placed at -4 meters. And we have a 3 kilogram mass placed at 2 meters. So like this. And let's find the center of mass of these things. So we know we're going to need the total mass, which is just the sum of all of these, 5 plus 3 plus 2, so 10 kilograms. Now we're going to need the moment about the y-axis, or the moment about x equals 0. So I'll write that m sub y for moment about the y-axis. So this is, right, we just do, since we're taking the moment, measuring the moment about the y-axis, about x equals 0, we just use these positions as they are. So mass 2 times position 3 plus mass, which is 5, times position -4, plus mass, which is 3, times position 2. So 6 minus 20 plus 12. So that is -2, and this is going to be in kilogram meters. And then the x-coordinate of our center of mass is just our moment about x equals 0 divided by the total mass. So this is -2 kilogram meters divided by 10 kilograms. Notice the kilograms cancel and we get something in meters, which is good because x is a position, it should be in meters. We get -1/5 meters. So it looks like the center of mass of these things is just to the left of 0. So if you balance this whole, if you put this whole system on a pivot point at x equals -1/5, it would balance there.